we'll be analyzing and sketching graphs. Now, if we take a look at what the first question asks is, how is the graph different from other graphs you have studied? So if we take a look at this graph, it's quite different than our other ones that we've had before, because there's lines, which kind of makes me think linear, but the problem is that they go at angles. So we can't call it linear. We can call each section linear. Oh, if I think about it, each section, I can think about this as 1, section 2, section 3, and section 4. So this kind of has 4 parts to it at doing different things. Well, 1 and 3 are very similar in that they're horizontal parts, but they're at different levels, so they're going to be at a different thing. So they're different, that they're not linear. The pieces are, but they're not exactly linear, otherwise it would be a straight line consistent all the way through. So we need to write a short paragraph that describes the water level changes over time. So I'm thinking we have water level here, we have time. So the water level is staying constant. So it's staying at the same level over time. And then right here, what happens? It increases, but we also think about that it increases at a constant rate. So I'm thinking when I write my sentence, I'm kind of thinking into parts. So the first part was the water level stays the same, stays the same level for some time. Part 2, the water increases. Now, we don't want to just say increases because there's different ways to increase, but this one, it increases at a constant rate. And we can even put in there of change. So that's kind of like we're talking about the slope, but we don't want to say just a positive slope, which we did, is we said positive as an increase, and then we use the word constant rate of change. It increases at a constant rate of change. Now, what happens up here at 3, our third sentence would be, oh, it reached a high level. The water stays level at a high water level. And then fourth, the last part, it drains out at a constant rate. So the water drains out at a constant rate. So that's kind of our paragraph. Sort of I like the bullet point parts for these, but you could write it as a full paragraph if you wanted to. Now, question C, what situation can this graph represent? I maybe think a water level in a bucket, or maybe in the sink doing dishes or something. Maybe I like that one, water in a sink. Now, a little bit different. It's a water in a sink, but it's not draining out all the way, because see how where it stops here? It stops back, at the same level that it started. So maybe so the water drains at a constant rate, and I'm going to put an and here now that I thought about it. So, and stops at the same level it started at. So notice how I kind of went and answered another question and then thought about it, kind of cued me in on more information about the graph. So I went back and edited my sentences so that it meant more information. The next part, so if we go to the next part, the graphs represent the speed of two cars. One is approaching a stop sign. The other is approaching a yield sign. So we have graph A. Here's our speed. Oh, they both have speed. This one is, oh, it's kind of a curved line. Oh, and this one is a linear, which has that constant rate of change. So I notice that they're both kind of going down. So the speed is decreasing. So how are they? Oh, how are they similar? They both have speed and time as their labels. They also decrease, I said, so they both are decreasing. How are they different? Well, I did explain one is linear with a negative slope, and one is curved. So part B, compare the steepness of each graph. So the steepness, remember, I kind of know from my linear is this constant rate of change, which is that slope steepness. So I'm kind of thinking that it's got a little bit more rise, so it is a little bit steeper. The curved line is very interesting for the steep. So it's here, it's really steep. And then what happens? Here it's kind of getting slower, like less steeper. And down here is not steep, not so steep. And it's almost kind of slowing down, really slow down here. So that's kind of how it looks for that steepness. So we'll label this one a constant steep. Well, not as steep as the steep, so we call it the less steep, constant less steep, because I think this one up here is a lot steeper than this one. So if we call this steep, it wouldn't kind of match that one. It kind of has to be a less steep. So which graph do you think represents the car approaching a stop sign? So when you stop at a stop sign, you're going to slow down. So the car slows down. So think about, kind of put yourself in a car and you're slowing down. So this speed is slowing. Let me get a different color here. This speed here is slowing down fast. So they're really pumping the brakes right now. So you're kind of getting thrown ahead, and then you're going to be slowing down. So they're easing off the brake a little bit, so it's not so bad. But then what happens if you're stopping at a stop sign? Here, notice your speed. The speed is still going. So if you were right here at the stop sign, what would happen? You would still be going through the stop sign. And the police would not like that at all. So if you're at a stop sign, you have to stop. So if we take a look at the second graph, I kind of like drivers that slow down at they're not throwing me forward like this person did up here. It's kind of a nice gradual slowdown. It's constant, a nice constant slowdown. And then right here, the speed is 0. So that means we stopped at the stop sign. Now this one, let's put a little marker here, did not stop at the stop sign. So it's a lot of like looking at the details, and notice how we used what we knew about graphs and the zero that we've talked about in the past, that it getting to that zero where this one didn't get that to that zero. So that's how you have to analyze graphs. All right, so the next one is the graphs show the temperatures throughout the day in 2 cities. So we have Belfast, Maine. So we have one in Maine, and we have one in Oregon, Newport, Oregon. So they both have temperatures, and they both have over time. So we want to describe the temperature in each city. So let's look at Maine first. So if we take a look at the temperature in Maine, so the temperature starts at a temperature, whatever this temperature is here, and from there it's going to go up. Oh, pretty quickly it's going to go up, but then by about, say, midday or a little later than midday, it kind of gets to its highest point. So it's warmest part of the day right here, that warmest part of the day, and then the temperature starts to decrease. But it starts to decrease, slowly decrease here, because it's not that steep. And then it starts later on. Oh, it's probably getting dark here because there's no sun to heat things up. So it's getting really cold fast. And then what happens at the end of the day? Oh, if we take a look, remember, like we did last time, it ended warmer than it did starting the day. Okay, so we could talk about those pieces as we kind of walk through that. If we needed to write a paragraph. So if we look at Oregon's Newport, here the temperature starts high and then decreases at a constant rate. So it's not linear, but this section, this we could call number 1, section 1, decreased at a constant rate. So the temperature dropped at a constant rate. Then right here, this second part 2, the temperature stayed the same. So it stayed exactly the same temperature, and then it increased. Now, looking at the decrease and the increase, it looks like the decrease was faster. So we can talk about this one as a faster decrease, but it's a constant decrease. And our increase was a constant, but not as fast increase. And where did it end up, the temperature? Well, we kind of look back over here, and the temperature ended up colder than the starting temperature of that day. So make through comparisons from the graphs. So we looked at the comparisons. So the Newport one has a lot of constant parts to it. The Main one doesn't have any constants, so it's increasing faster at the beginning of the day, then slowing down, then slowly decreasing, and then increasing faster, or increasing the decreasing. It's kind of confusing, but the decrease there's more decrease as it continues on through the night or the day, later in the day. All right, so now we're going to go into sketching a graph. So we kind of need to think about the situation and think about that graph that we're going to have over our we'll need two labels here. So a stopped subway train gains speed at a constant rate. Ooh, constant rate, that tells me a line segment until it reaches its maximum speed. It travels at that speed for a while and then slows down at another constant rate. That's going to be a line until coming to a stop. Ooh, that stop was important. Remember, with the stop sign problem with the car, so it's going to end on the line here. Oh, and that's the next station. So we're going to have speed of the train, because that's what it was said right here, speed of the train, and it's going to be, we're talking about time. Now, they didn't say time in here, but it's implied that it's going to be that time. All right, so the subway stopped at the train stopped at a subway trains, or stopped at a station, and then it sped at a constant rate until it reached its maximum speed. So it was stopped, so it hits here on the line, so it went at gained constant speed until it reached its maximum speed here. And then, so here it's not stopping at this speed, but it's going the same speed constantly. So that's why that it's not increasing or decreasing, it's just staying. So let's say it's going 50 miles an hour. It's going constant at 50 miles an hour. So it's not gaining or dropping or decreasing. So then it's slowing down at a constant rate. So usually I like a train to slow down slower. So I'm going to make it a less steep constant rate. So I'm going to make it a little bit longer going out here because I want my train to slow down a little bit more than actually speeding up faster, because I think when people are speeding up, it's easier for them to kind of know and start that it's starting to speed up. But the stopping, you want that to be a little more gentler, I guess. Oop, my line went hooking up. So, and notice that it stops right here. So we're going to sketch another graph down here. And as television size increases, the price increases at a increasing rate. Ooh. Okay, hold on. So let's get the television size. So we'll put the size here first because that's what you buy first. The size of the TV. And over here is the price. So, I think if we have a zero price or zero size, we're going to have a zero price. We're not going to be able to buy it unless you want to buy it. So now it says the price increases. So it's going to go up, but it's at an increasing rate. So that means it's not going to be a straight line, because if it was a straight line, it would say at an constant rate. So it's increasing. So I'm thinking a smaller TV, like really small, teeny ones, wouldn't be too expensive. But then as they get bigger and bigger, it's going to increase more and more. So that's that curved line. And then, ooh, look at there. It just keeps going up and up and up. Now, I made it a little bit too steep, probably. So it probably would be more like a lesser kind of curve. But see how it's getting steeper and steeper? So that increase is increasing. That's what that means right here, our increase of an increase. And I know it's a little confusing to think about, but because it's shallower here, it starts slower. The prices go up slower. But as your size gets bigger and bigger, so from like a half a wall to a big sized wall screen, it gets more expensive because there's more things you have to put up for it. And our last one is to describe the relationship between the two quantities. So I have a balloon and hair. I think I'll do the hair one first. So we have our length and time. So our hair length increases at a constant rate. Oh yeah, my hair grows constantly. And then why would it jump? What do you do to your hair? Oh, there's a haircut. So we get our haircut and it gets put back to the same length that you have before. And then it increases at a constant rate. And then we get a haircut again, back to the same spot. And then it increases at a constant rate. So a balloon now over here, if we think about our balloon, so our volume of our balloon. Oh, so we're taking a nice, like, I don't know, red balloon that we're going to blow up maybe. And we breathe into it. Now we're breathing at a constant rate. So when you blow air into it, you're blowing constantly. And then what happens right here? Before we blow again, you have to take a breath. So this is a breath of, as you're holding it. Now you're not letting the air out, otherwise it would go down here if you let out the air, but it's holding steady in there. So you pinched it and then blew at a constant rate, pinched it again, there's another breath, and then blew a third time. So how we know it's a third breath is because there's one breath here, breath in, and two breathe air into the balloon, and the third breath into the balloon. And that is analyzing graphs and sketching graphs.